without further ado, we'll go straight on to Vadim. Oh, is it just gone? Oh. Don't do that. Over to you to talk about the semantics of CHERI C.
Okay. I'll be talking about formal mechanized semantics of CHERI C. This is joint work with my co-authors. And this is funded by these nice people. So CHERI C is a de facto C dialect, as Jessica explained. Is defined by the C-lang LLVM-C compiler fork. That's kind of the most mature definition of compiler we have for CHERI C, which supports multiple backends, Armorella and CHERI C in particular. And it's evolved. It was experimental development, so they tried to compile a bunch of code and they see what works, what doesn't. So when we approached that, we very seriously looked at that and we take into account their experience because it was come from the porting actual real code. Yet some features still experimental or optional, like sub-object bounds mentioned earlier. There is a CHERI C programming guide, but it's not exhaustive language specifications, more an introductory document, which is a good one. And now we have 3 compilers, C-lang, GCC, and there is CHERI compiler from Microsoft, which is based on the fork from C-lang. And obviously, we need to think about the language definition to make sure that we have talking about the same language across these compilers. So our goals in this project was to review design decisions taken by these CHERI C implementations, compare them with each other, analyze their potential impacts. And then we wanted to propose a comprehensive CHERI C semantics definition in the ISO C language, prose language, the same language as the standard is written. But being formal people, I don't think it's sufficient to have this English language standard. We would like to have also executable mechanized semantics, formal semantics of CHERI C, which will be the goal definition of the standard whenever the language is not clear. And we would like to, wanted to implement such executable semantics, and executable means you can run small programs and see how they operate in CHERI C. That's what we taken, that was our goals. So quick reminders, pointers versus capabilities. On the left side, you see our old good CHERI pointers. In this example, using 64-bit example. And this is just integers. They can be manipulated anyway. They don't have any integrity protection, and they don't have a protect against inappropriate use. On the right side, you have capability when you add to the 64-bit address some metadata, like bounds and the validity tag, and it's control how they can use permissions, for example. And the bounds control what range of memory addresses can be accessed through that. And the tag protects the integrity of the capability. If you modify it inappropriately, the tag will be cleared and it will become unusable. I'm talking about C language here, not about lower level CHERI architecture. And the big part of C language semantics is undefined behavior. And undefined behavior, if you read the spec, this is a definition of defined behavior. And the first line, and the common examples of undefined behavior is out-of-bound memory access, signed integer overflows, and data races. It's very difficult to deal semantically because if any execution abstract machines result in the undefined behavior, the behavior of the whole program is undefined. And in particular, if you are able to detect undefined behavior in some particular point of execution, it doesn't mean that up to this point, the behavior of the program defined. It's undefined even before that. It's so-called time-traveling undefined behavior phenomenon. So in CHERI C, more special safety issues are prevented by CHERI. They correspond to UB in ISO-C, undefined behaviors. So if you have this perfect program in ISO-C which doesn't have any exhibit any undefined behaviors, you're good. However, when they happens, it's tempting to treat them deterministically. Say they're no longer undefined. We know what happens. If you try to write out of bounds, you get an exception or fault. However, this conflicts with a lot of optimization which existing compilers do, because compilers optimize your code under the assumption that undefined behavior shouldn't happen, and if you make it deterministically, it happens. Deterministic handling of the situation. The optimization breaks, and you lose either you lose performance of your code, or you have to modify your compilers to make sure these optimizations are not happening. So CHERI C is a basic idea: just replace pointers with capabilities, implement pointer arithmetics on capabilities. Hardware takes care of all the permissions and bounds, and integrity. And compiler will set capability bounds for local variables when you take the address to the bounds of their stack slot. And the runtime linker and allocator set the capability for globals and function pointers and heap allocations. So it sounds straightforward enough. Let's look at some examples. So the first question, what's pointer equality? And we can think about several definitions. We can just compare all 129 bits, and seems like very logical thing to do. You can say, okay, maybe tag integrity is not part of that. You compare 128 bits, or maybe you can compare only addresses. And there's a blue check mark there. It's a hint. It's a spoiler that that's what we ended using as a definition. Because it turns out if you try to compare all metadata in the pointers, it breaks a lot of existing code. So and one of the goals of CHERI C was to make its existing code easily portable to it, and so bitwise equality breaks that. So address equality is what we choose. But we have to keep in mind that doesn't mean that interchangeability. If two pointers are equals, according to equals operator, they're not necessarily interchangeable because they can have same address but different metadata. It's tricky. Another example is out-of-bound memory access. So what this program on the left does, it it forms a pointer which is one pass of the stack allocation of variable x and try to write into it. So in ISOC, the constructing one pass pointer is permissible, it's fine. Accessing it, it's undefined behavior. So line 3 is undefined behavior. Although conventional compilers, most compilers will just offset the address level write at x plus size of, and that will be out-of-bound memory write, which will cause all these security problems. In C language, taking address of x will return the bounded capability with exact bounds of the stack slot allocation for x. Adding size of to it will just change the address part, but doesn't change bounds. And then you try to write into the line 3. If it happens, the hardware will prevent it. So security problem averted. Seems easy, not so much. If we enable -O2 optimization, this code just returns 0. It will not attempt to write or modify pointers. It just optimizes out everything. So, for example, deterministically, if you say that this program will always calls exception, that's not true anymore. If you make the x as global variables instead of the local, with O2, it start to still try to write it, and will get out of bounds exception. And then if you increase optimization to -O3, even with global, it will optimize it out again. It will not write to again. So depending on the optimization language levels and combination of locals and globals, you can expect different behavior. And this is an example of semantic problem we have to deal with. I don't give you an answer how we deal with it. We don't have enough time for that. I'll encourage you to read the paper and specification we wrote. Another example is modifying the pointer. So modifying the bytes of the pointer is permissible in ISOC. We take some byte of the pointer and we overwrite it with itself. So from ISOC, it's perfectly fine. In CHERI C, we also allow bytewise access to data containing pointers. That's fine. But modifying it should clear the tag because it can potentially affect the integrity of the capability. You shouldn't allow to force the capabilities. The hardware usually prevents you from doing that. But what about memcopy? Can you write your own version of the memcopy just as a loop copying byte by byte? With this, you're no longer able to do it because you won't be able to copy the pointers without invalidating them. Also, optimizing compiler might eliminate the byte write at line 6. So at line 7, depending on optimization levels, the pointer may be valid or may be invalid. So we don't know. And what about clearing the tag? Should be cleared in this particular case because we're not changing the value of the capability. It will be still same value, writing with the same byte, but just attempt to write it should invalidate it, or the value change should invalidate. That's another question we have to ponder. And finally, because of the compression, if you try to describe the impact of modifying the byte of capability, you should keep in mind that depending on the compression scheme, which may be dependent on the target architecture, it can affect one or more multiple fields of the resulting capability. Final example, I think Jessica touched upon it. It's about capability derivation. So a very simple example, we're taking two pointers, convert to the in PTRT and add them. And in ISOC, it's very straightforward. C0, the result of addition, and C1 is exactly equal, and the interchangeable. It's exactly the same. In CHERI, when we're adding two capabilities, obviously we will add their addresses, but we need to choose one of the meta information, which one we use to derive the result. We couldn't use both. They have different bounds. So left-hand side seems to be a reasonable choice, but few issues arise here. In CHERI C, the C0 and C1 will be equal according to the equals operator, because it compares only addresses, but they're not interchangeable because they have different meta information. Non-representability can emerge, and in this case, they both in P30, but if one of them is integer, like for example 1 plus a, we want to make sure that the result will be still a capability, not just integer, because otherwise it won't be able to convert it back to the pointer. So there is integer conversion rank and the rules in the standard we have to take into account, and we have to modify them to make sure that they take into account this situation. So this is just examples, so just to show you that it's just plugging in the CHERI capabilities into the C pointers. It's not end of the story. There is a lot of issues to be considered, and some of these issues we did consider, and we hopefully addressed is listed here. Now we did the word about executable CHERI C semantics. We used Cerberus ISO semantics. So Cerberus, if you're not familiar, is an executable semantic of the C, very mature semantics. It's implemented through the elaboration. So it takes the C programs and converts them to the smaller core language. And in this core language, a lot of things which are implicit in the C language, like out of bounds check or typecasts, becomes explicit. So it's much better defined language. And this is the language we can reason about. So part of the semantic is a memory model, which defines all the memory operations and operations on the pointer. When we adapted this Cerberus ISO semantics to CHERI C, most of our modification was to the memory model, 90%, 95%. And we implemented it in COC because we wanted to do some formal proofs about that. But to be able to have executable semantics, we extracted this COC back to a camel linked to the rest of the Cerberus framework, so now we can run executable semantics to run small program. As a particular model of the capability, we have to use some concrete one to run code. We used Morello capabilities format, but any other can be plugged in easily. Then we developed a test suite, and now about 94 tests for different CHERI C semantics issues as we were analyzing and discovered it. And we run it against all the compilers we can get our hands on. Our Cerberus executable semantics, Silangel LVM for both Morello and RISC-V and GCC, and across different optimization levels and different flags. Good news, there is no major incompatibilities with proposed semantics were found. There are some minor bugs and some discussion about error messages formulation, but no core disagreements. So I think we're good here. Bugs were reported back to the compiler developers. So where we can go from here? So what we're working on right now is a formal comparison of CHERI C memory model with ISO C plus PNVA AADI memory provenance memory model. So because there is some overlap there in C pointer provenance and CHERI C protections, we would like to see how they related, if there is any redundancy there, or if one covers another. We also work on formalization of revocation mechanism, cornucopia, and that is leading to be able to do some proof on temporal safety properties of CHERI C, or memory model rather, because we just have a memory model. Some longer term ideas, we're not working yet, but it would be nice to work, and if anybody here is interested in working and discussing it, please talk to us. Proving additional properties of CHERI C in the memory model. Now we have it formalized in COC. Anybody can take it and prove things like good variable laws from CompCert, reachable capability monotonicity. It would be nice to have, if we have formal semantics of Cerberus core language for CHERI C, just ISO C, it will allow us to reason about the programs. Now we can reason about memory model. If we like to reason whole programs, we will need semantics of the core. And if we have formal semantics of CHERI LLVM IR language to which it compiles, for example, using Vellum project, which already have a good start on the IR semantics, it will allow us to reason about the code generation and compilation and optimization. So we can have the full pictures on both sides. So to conclude, there are two publications we have here. We would like you can take a look. The first is a paper which is accepted as POCL'24. You can have a preprint, take a look at the preprint, and which describe our journey and some of the semantic decisions we make, how we address this problem I showed before. And the second is a technical report, which is extension of ISO standard in the prose, similar to the ISO standard. So if you're reading ISO standard, you can read that. If not, I don't. So the project is on GitHub, open source. You can see, anybody can see it. You can play with our executable semantics to save you the trouble of installing all the dependencies and compiling it. There is a Docker image, so you can run it on the small programs. We also did the first integration to the compiler explorer, executable semantic. So it's not hosted anywhere, so it's also a Docker, but you can run it with this command and play with it on your machine. And there is a CHERI C semantics test suite, which is also on GitHub right now. That's all. Thank you.
Thank you, Vadim. Got a question at the back already. Oh, Mike is coming. So, Mark?
Your pointer equality didn't include the validity bit when you were comparing capabilities. Is that true for like atomic compare and swap instructions as well? Do you know what they do?
Is it true for what?
The concurrent atomic compare and swap instruction. It does a comparison of, if I put two capabilities into it, what I'm curious about is what parts of those it will compare.
So this is C language operators, so the instructions.
Yeah.
So we work on the level of the C semantics.
Oh, okay. Sorry.
Jessica?
So I forget what Morello's instructions do. On CHERI RISC-V, the semantics are the same as C standard equality. It is a contentious issue because both things are useful in different cases. And although you can have instructions that support both, and obviously the LBM IR can potentially support both, how to expose that to C is a bit of an interesting question because there is only one atomic interface in C that you have to pick which it does. So, yeah, it's a good question.
But underlying will make it accessible.
Well, at the moment on CHERI RISC-V, we don't provide either as an instruction. We just do load link store conditional loop, so you can put whatever you like as the comparison in the middle. On Morello, they give you one of them, and I think it might be exact equality even potentially. I couldn't tell you off the top of my head, but there's no reason you couldn't have both in the architecture, and you may well want both. But if you put instructions in the architecture that aren't exposed directly to C, it's a lot harder to justify. And I think there's a question there of how you properly expose them, whether that's with some new intrinsics or what.
There is intrinsics, right? There is intrinsics for exact comparison. Here's in the footnote.
Might pass you over to Ian next.
The test suite, you mentioned running it on different compilers. Would it be appropriate to run it on the CHERI compiler, even though, I mean, I know that the Cerberus model wouldn't be valid, but the C semantics?
So we thought about it. It will require some work because the runtime is different. They don't have like POCL runtime like with printf and main. So they have this.
But they have C.
Yeah, but I suppose that with some additional work you can build some harness to run this on the CHERI, but it's additional work. We haven't done it yet. Mm-hmm.
Good.
Okay. I think in the interest of time, we'll move on. Thank you very much, Vadim.